So today we're going to talk about section 4, the cross product of two vectors in space. We discussed the dot product or uh, scalar product or inner product of two vectors last time. Um, we're going to discuss another form of modification of two vectors. When you define modification of two vectors, you have different ways to do it. Uh, we just talked about the dot product last time. Today we're going to talk about another form of multiplication of two vectors that's called cross product, also referred as vector product. Okay, so by the name you can imagine that you're going to get the vector from the cross product. You get the number, you get a scalar from the dot product. But for cross product, you're going to get another vector, okay? But before we discuss the cross product, we need to introduce the determinant of matrix. I don't know if you learned it before or not. So what is a matrix? A matrix, excuse me, is a excuse me, you know, arrays of numbers. You got rows and columns, okay, in a matrix. Each row will have a bunch of numbers, and then you just have a bunch of rows and columns. And well, you can call that arrays, all right, of numbers. And then you use parentheses to denote a matrix. And then you define the determinant of a matrix for square matrices. Okay, you talk about the determinant of square matrices. That means you have same number of the columns of numbers in the matrix, and we have to define the determinant of matrices from the very basic 2 by 2 matrix. And then based on that, we define the determinant of 3 by 3 matrices and so on. So what is the determinant of a 2 by 2 matrix? I suppose we got matrix A, B, C placed in the rows and columns. You got 2 rows and 2 columns. Okay, so we call that 2 by 2. It means 2 rows and 2 columns. So the determinant of this matrix denoted by the vertical bars instead to replace the parentheses of the matrix. And sometimes people also use det of the matrix followed by the matrix. Det, for example, if I call this matrix the 2 by 2 matrix A, B, C, D, A, capital A, then we can write det capital A to mean the determinant of that matrix. But you can also use the vertical bars as we did in here. So that's called the determinant of a matrix, and for a 2 matrix ABCD is the difference of the cross product, the cross product of numbers. So multiply A with D and subtract B times C. So that's the determinant of this 2 by 2 matrix. And then you can define a determinant of 3 by 3 matrix based on the 2 by 2 matrices. So let's say we have a 3 by 3 matrix, 3 rows and 3 columns. We call them A1, A2, A3 for the first row, B1, B2, B3, the second row, and C1, C2, C3 for the third row. Okay, so what is the determinant of this matrix? You again use the vertical bars uh, to replace the parentheses of the matrix. Okay, you can find the determinant of this 3 by 3 matrix by expanding based on the first row, for example, in here. What you do here is pick up the first entry or element, A1. That's the first row and the first column entry or element. And then if you just cross or delete the first row and the first column, you're left is just B2, B3, and C2, C3, right? So just multiply A1 by the determined with the 2 by 2 matrix B2, B3, C2, C3 obtained from deleting the first row and the first column, which were A1 seats. And then you go to the next entry on the first row A2, but you change the sign, so it becomes minus A2. Again, you're going to delete the first row and the second column because that's how where A2 is located. So if you do that, what you're going to have will be a 2 by 2 matrix B1, B3, C1, C3. So you multiply A2 by the determinant that matrix B1, B3, C1, C3, a 2 by 2 matrix. And then you go to the next element or entry in the first row A3, and you come back to plus sign. Okay. Remember when we do A2, you subtract, but when you add A3, it becomes positive again. And then just do the same thing. You delete the first row and the third column. That's how A3 is located, right? And then you get the two matrices B1, B2, C1, C2. So you just multiply A3 with the determinant of this 2 by 2 matrix B1, B2, C1, C2. Now we know how to find out the determinant of 2 by 2 matrices. So we got 3 2 by 2 matrices in here. So you just use the definition of the determinant of 2 by 2 matrices to compute them. For example, the determinant of B2, B3, C2, C3, this 2 by 2 matrix will be B2, C3 minus B3, C2. So you just multiply A1 with that. In the second term, you just multiply A2 by the determinant of B1, B3, C1, C3 with B1 times C3 minus B3 times C1. And then you add A3 times the determinant of 2 by 2 matrix B1, B2, C1, C2, which is B1, C2 minus B2, C1. So at the end, you're going to get a number. Okay, so that's the determinant. And then you can do, determinant of 4 by 4 matrix, 5 by 5 matrix in a similar way, just to expand based on the rows, the first row, for example. So that would be similar to 3 by 3 matrices case. All right. And then we can use the notation or operation of matrices, the determinant of matrices, to define the cross product of vectors. Okay. But let's just do a few examples of determinant of matrices. So for example, if you want to find the determinant of a 2 by 2 matrix, a 2, 1, negative 6, 4, you're going to multiply 2 and 4 and subtract the 1 times negative 6. Okay? The current definition. Just do cross multiply and subtract. 2 times 4 is 8, and the negative 1 times negative 6 is positive 6. You get the 8 plus 6, which is 14. Okay. Uh, how about the 3 by 3 matrix? So this time we finally determine those 3 by 3 matrix. 1, 2, -1, 3, 0, 1, -5, 4, 2. You just expand by the first row. So you pick up first number right on the upper left, which is 1, and then you delete the first row and the first column. You're left with a 2 by 2 matrix 0, 1, 4, 2. And you just multiply 1 by the determinant of that matrix. And then you go to the second entry in the first row, which is 2 by the select. So you minus 2 and then times the determinant of the another 2 by 2 matrices obtained from deleting the first row and the second column. That's where two seats, right? You just delete the first row and the second column. So you get a 3, 1, 5, 2. That's 2 by 2 matrix. So you multiply 2 with that determine the matrix. And then you go to the third entry in the first row, which is -3, and you add. So that's plus -1 times determine another 2 by 2 matrix, which is from deleting the first row and third column. Okay, -1 is on the first row on the third column, so you delete those, and then you get the 2 by 2 matrix 3, 0, -5, 4. So -1 times the determinant of that matrix. Okay, and then you just compute the determinant of each 2 by 2 matrix in the problem. So the first determinant of 2 by 2 matrix is 0 times -1 times 4, and the determinant of second matrix is 3 times 2 minus 1 times -5, and the determinant of the third matrix is 3 times 4 minus 0 times -5. Okay, so you just do the simple algebra a little bit. 0 times 2 is 0, 1 times 4 is 4, so you get 0 minus 4 in the first term, and 3 times 2 is 6, -1 times -5 is +5, so you get 6 plus 5 in the second term. And 3 times 4 is 12, and 0 times -5 is 0, so you get 12 plus 0 in the third term. And then you just simplify a little bit. So 0 minus 4 is -4, so you get 1 times -4, which is -4. And then you get a 6 plus 5, which is 11 times 2, so you get 22, and that's minus. And then 12 plus 0 is 12, so you get 1 times 12, 12 also, and you also subtract. And then you get -4 minus 22 minus 12. And if you do that, you can get -38. Okay, -4 times 22 is -26, and then you subtract 12, you get -38. So that's the determinant of the 3 by 3 matrix in this example. All right, so pretty straight. I'm sure you know something of this things before. So now we can use the determinant to define the cross product, as I said. Okay. So suppose we got two vectors, A and B, with components A1, A2, A3, and B1, B2, B3. And then the cross product, the A cross B, okay, is denoted by A cross between the two vectors A and B. And you got the, another vector from this cross product. And the X component of this cross product is A2B3 minus A3B2, and the Y component of this cross product is A3B1 minus A1B3. And the Z component of the cross product is A2 minus A2B1. So you don't have to memorize this, because we're going to use determinant to represent this cross product. So let's see how we can do that. Okay, so if you rewrite this cross product components, with the unit vectors, then you get A cross B equals I times A2B3 minus A3B2 minus J times A1B3 minus A3B1. So I just negate the Y component. So it becomes A1B3 minus A3B1. Okay. And the sign becomes negative in front of J. All right. And then K times B A1B2 minus A2B1. All right. And then we can rewrite each number by using the determinant of 2 by 2 matrix. So for example, A2B3 minus A3B2 we can rewrite as determinant of A2, A3 and B2, B3, that matrix. You can easily check that. And A1B3 minus A3B1 is also a determinant of a 2 by 2 matrix A1, A3, B1, B3, right? And then A1, B2 minus A2, B1 can be also rewritten as the determinant of the matrix A1, A2, B1, B2. Okay, if you check it. Well, then you, if you remember the definition of determinant of 3 by 3 matrix, it turns out that you can rewrite the whole thing as the determinant of those 3 rows, the matrix with those 3 rows. The first row will be I, J, and K. The second row will be A1, A2, A3. The third row will be B1, B2, B3. You can easily check that backward, okay, instead of going forward. You can expand this determinant by the first thing you're gonna get I times A2, A3, B2, B3, the determinant of that, right? And then minus J times A1, A3, B1, B3, okay, and then add K times A1, A2, B1, B2, the determinant, okay, if you delete the rows and columns. So, and that's what we have exact for A cross B. So at the end, to compute the this matrix, you can find the cross product of 2 vectors. So in other words, to find the cross product of 2 vectors, you just evaluate the determinant of this 3 by 3 matrix, where the first row will be the unit vectors A, I, J, and K. The second row will be the components of the first vector A, and the third row will be the 3 components of the second vector B in the cross product. All right. So let's just do one example to find the cross product of 2 vectors. So A equal to 5, 1, 4, and B equal to negative 1, 0, 2. So when you find the cross product of A and B, so A cross B will be just equal to the determinant of this 3 by 3 matrix, IJK, A1, A2, A3, B1, B2, B3. So we just plug in those numbers. A1 equal to 5, A2 equal to 1, A3 equal to 4, B1 equal to negative 1, B2 equal to 0, B3 equal to 2. Okay. And then you just expand this then by the first row. So you get I times the determinant of the 2 by 2 matrix 1, 4, 0, 2, and then subtract. Okay, go to the next entry in the first row. You get a negative J times the determinant of the 2 by 2 matrix 5, 4, negative 1, 2, and then plus go to the next entry in the first row. You come back to the positive again. So plus K times and the determinant of the and another 2 by 2, 5, 1, 0, 1, Z, and 1, 5, 1, negative 1, 0. And then you just compute the determinant of the 2 by 2 matrices. Okay, so the first matrix, the determinant of that will be 1 times 2 minus 4 times 0, and the determinant of the and in the middle will be 5 times 2 minus 4 times negative 1, and then the determinant of the third term 2 by 2 matrix will be 5 times 0 minus 1 times negative 1. Okay. So now then what? 1 times 2 is 2. 4 times 0 is 0. So you get 2 times 0 in the first part. And then 5 times 2 is 10. 4 times negative 1 is positive. So you get 10 plus 4 in the second term. And then 5 times 0 is 0. Negative 1 times negative 1 is 1. So you get 0 plus 1 in the third term. So at the end, the 2 times 0 is 2, so you get 2i. 10 plus 4 is 14, so you get 14j, but it's negative. And then 0 plus 1 is 1, so you get 1k or just k. So at the end, the cross product of those two vectors is just 2i minus 14j plus k. All right? Well, there are some important properties, for the cross product. For example, if you try to take the cross product of the same vector, A or B, any vector, you get a zero vector. Okay. So let's just verify that by using the determinant. So A cross A just determine the 3 by 3 matrix IJK A1, A2, A3, and A1, A2, A3. So then you just explain this determined by the first row, you get I times the determinant of the matrix A2, A3, A2, A3 minus J times determinant for the 2 by 2 matrix A1, A3, A1, A3 plus the K times the determinant of 2 by 2 matrix A1, A2, and A1, A2. So if you just compute each determinant of 2 by 2 matrix, you get I times A2, A3 minus A3, A2 minus J times A1, A3 minus A3, A1 plus K times A2 minus A3, A1. And then you can see, each term you just get everything subtracted by itself. A2, A3 is the same as A3, A2, A3, A2 because you're multiplying two numbers. It really doesn't matter the order. And similar for the other two terms. So you get zeros all the way down. Then at the end, you just get a zero vector. Okay. So the cross product of a vector by the way is zero vector. Okay. So that's the important property of vector products. Okay. Just like the cross product. We can have another way to find the cross product of two vectors, from the magnitude of the vectors and the angle between the two vectors. Okay, but let's just figure out the direction of the cross product of A and B first. The difference between cross product and the dot product. One of the differences is, we get a vector from the cross product. So this time we need to find out the direction and the magnitude of the cross product because it is a vector, right? So the theorem says, so there are two theorems here. The first theorem says A cross B, so that's as we said, A cross B is another vector. So this vector is orthogonal to both A and B. Okay? And so it will perpendicular to the plane determined by A and B. That means, and also A cross B obey the right hand rule. So what it means by that? Okay, so if you curve, if you hold your right hand and let the thumb point into the upper direction, okay, and you just go, from A and B, from the vector A to vector B, and that's the direction when you curve your fingers from A to B. Okay, so in this case it will be counterclockwise from A to B. Rotate counterclockwise. So you just hold right hand curving like this, and then the thumb direction will give you the direction of A cross B. So that's how you determine the cross product of two vectors, the direction of that. Okay, so that's called the right hand rule. Okay, so that tells us how to determine the direction of A cross B. But then the other thing is how do you find out the magnitude of A cross B? Okay, it turns out the magnitude of A cross B is just the magnitude A times the magnitude B times sine theta, where theta is the angle between A and B. Okay. Now you can see, you know, if you consider, you know, B times from the graph on the right hand side, you can see the magnitude B times sine theta will give you the height of the parallelogram shown in the graph. Okay, formed by the two vectors A and B. So then the magnitude of A cross B is just the magnitude of A times the height of the parallelogram. So you got the base times height, you get the area of the parallelogram. Okay, so the cross product can be used to find the area of a parallelogram. All right, and if you still remember the dot product, what's the magnitude of the dot product? Is the magnitude A times magnitude B times cosine theta. Okay, so that's the only difference between those two product, two types of products in terms of the magnitude. Okay, so these are some important results. Okay, let's see. You know, one of the things then we can, you know, use the theorem in the last slide that automatically tells that two non-zero vectors A and B are parallel if and only if A cross B equal to 0. Well, because when A and B are parallel, then the angle between those two vectors are 0 or pi 180 degrees. But the magnitude of A cross B is just the magnitude A times magnitude B times sine theta. So you get either sine 0 or sine 180 degrees, which is 0. Again, both are 0. So then you get 0 vector for these two you know, vectors when you do the product, cross product. Or if you know the cross product is 0, then because again using the same formula, you know, the magnitude A times magnitude B times sine theta, then because you know A and B not 0, then theta must be equal to 0 or 180 degrees in order for sine theta equal to 0, right? Okay, so that means the two vectors are parallel in that case. Okay, or anti-parallel, you know, we can call both are parallel, even that, you know, it's anti-parallel. Sometimes we can call it parallel in general. Okay, so let's just do one example. I'll find a non-zero vector orthogonal to the plane through the points PQR and find the area of triangle PQR. Okay, so so that's one of the applications of cross product. You can find the area of a triangle. All right. So we got 3 points in 3D space, and we want to find another vector orthogonal to the plane determined by the 3 points PQ and R. How do you do that? We can use you know, vectors and use the cross product. So first, let's just try to draw a vector from P to Q. So the vector PQ will be -1, -2, 3, -1, 4, -5 as the components. Remember, terminal minus initial points, the components. Do the subtraction of components. So you get -3, 2, and -1. So that's the vector PQ. And then you can draw another vector from P to R to get another vector. So the components of this vector will be 3 minus 2, 0 minus 1, 6 minus 5. Okay, again, the components subtraction uh, terminal minus initial. Okay, 3 minus 2 is 1, 0 minus 1 is -1, 6 minus 5, 1. So we get another vector PR. 1, -1, 1. And then why don't we just do the cross product with these two vectors? So we get the determinant of ijk, -3, 2, -1, 1, -1, 1. And then, just use definition by the what? The determinant. So you get I times the determinant of 2 by 2 matrix 2, -1, -1, 1, minus j times determinant of 2 by 2 matrix -3, -1, 1, 1, plus the plus k times the determinant of 2 by 2 matrix 3, -3, 2, and then you just do the 2 by 2 matrices again. So you get 2 times 1 minus -1 times -1 in the first time in the first part, -3 times 1 minus -1 times 1 in the second part, and -3 times -1 minus 2 times 1 in the third part. And if you do that, you get a 2 minus 1 in the first place, -3 plus 1 in the second place, and then 3 minus 2 in the third place. So after simplification, if we do these numbers, you get 1i plus 2j plus 1k, but you don't have to write the ones. So it's just I plus 2j plus k. So this is the cross product of PQ and PR, those two vectors. So why do we want to do that? Because we need to find the non-zero vector orthogonal to the plane through the points PR. Remember, the cross product of PQ and PR is perpendicular to the plane of PQ and PR. So that means it's orthogonal to the plane determined by the points PQR, right? Okay, so so we got the first part finished, and then we need to find the area of triangle PQR. Remember, I just discussed a few minutes ago the magnitude of the cross product gives you the area of the parallelogram determined by those two vectors PQ and PR shown in the graph. So that means the magnitude of PQ cross PR is just the area of the parallelogram in the graph. And what we need to find is the area of the triangle PQR. What's the relation between the area of the triangle and the parallelogram? It's just half of the parallelogram. The area of the triangle PQR is just half of the area of the parallelogram. So what you do is just take half of the magnitude of the cross product, because the magnitude of cross product gives you area of the parallelogram. So the area of the triangle, which is half of the area of the parallelogram, so that's just half of the magnitude of PQ cross PR. So, but we already know PQ cross PR is just the I plus 2j plus k. So what you need to do is just multiply half by the magnitude of this vector, I plus 2j plus k. And the magnitude of this vector is just the square root of 1 square plus 2 square plus 1 square, which is 1 plus 4 plus 1, and which is 6. So you get the square x in here, and then multiply by half, you get a square root of 6 over 2. So the area of the triangle PQR is just square root of 6 over 2. All right? So it's very convenient to use to use some cross product in geometry. Okay, so that's this. There are some important properties cross product. So again, let's just start from the standard unit vectors I, j, k along x and y, z positive directions. And then we have the following relations. I cross j will be equal to k. Okay, so you cross two vectors again, you get another vector. It turns out that I cross j equal to k, and you can easily check this by the right-hand rule. Okay, from x to y, you rotate from x axis to y axis, and then your thumb would point to the z direction. So that gives you the confirms or verifies directions. But also, the magnitude, if you consider, all of them are unit vectors, and so the magnitude of all the vectors will be 1, but also the angle between x and y axis will be 90 degrees, so sine 90 degrees equal to 1 if you use the formula, for the cross product of the magnitude of I cross j is just the magnitude of I times the magnitude of j times sine theta. But the magnitude of I is 1, magnitude j 1, the sine 90 degrees is 1 also, so the magnitude of I cross j is 1, and the magnitude of k is also equal to 1. Okay, so that confirms both direction and the magnitude. And you can easily check the other relations, j cross k equal to I, k cross I equal to j, And if you do, the cross product in the reverse order, like j cross I, you get a negative k. Okay, if you use the right-hand rule, and the k cross j equal to negative I cross k equal to negative j. Okay, so how about the three vectors? They cross product, do it twice, like I cross j. So in here we do the I cross j first. Then you get the k. So then it becomes I cross k, which is negative j. Okay. And if you do I cross I first and then cross j, you're going to get 0 vector from I cross I because they are parallel, right? So 0 cross j, you get 0. So then you got different things if you change this order of multiplication. So you got I cross j in 2 different ways. But then you get the results. So that's a commutative and associative laws do not hold in cross product. Okay, so you cannot change the order modification in cross product, and you cannot do the 3 vectors cross product in different ways. They're not the same thing. Okay, so that's the difference between vectors and numbers or scale. So we didn't finish this section today. So I guess we still have a little bit to discuss. This will be a long section, and so we need more time. I guess I'm going to do it in next week. And hopefully we can finish everything by next week. We got another section to do for the whole semester, okay? But we're going to get it done, all right? We just got a little bit to do. So let me just stop here and, I'm going to take the road now. So